We're now going to cover the next topic in our overview of Java's key functional programming concepts and features, which will focus on immutable objects. An immutable object is an object whose state remains constant after it's been entirely constructed. After first covering the key concepts associated with immutable objects in Java, we'll then examine a case study that fixes the problems with the BuggyFactorial example we covered in the previous part of the lesson. This particular example can be found in the EX2 project, in my FP folder, in my modern Java GitHub repository. Functional programming focuses largely on immutable objects rather than the mutable objects that's the focus of object-oriented programming. An immutable object's state cannot change after it's been constructed. Take, for example, the money class shown here on this slide. The money class contains only final fields, such as mamount and mcur. Moreover, it only has accessor methods, such as getConcurrency and getAmount, that return mcur and mamount, respectively. However, it contains no mutator fields whatsoever. Instances of money will behave in precisely the same way throughout their whole lifetime. Therefore, immutable objects are forever, just like diamonds. Java string is a commonly used example of an immutable object that you've likely run across when writing Java programs. All of the fields in the string class are defined as final, such as the value field shown here, and it only defines accessor methods, such as the length method here. After the constructor of string sets the value, the string will behave the same throughout its entire lifetime. Now that we've discussed the concepts associated with immutable objects in modern Java, let's show how to apply immutable objects to avoid shared mutable state. In particular, immutable objects help to eliminate shared mutable state in parallel pipelines. For example, the parallel stream factorial class shown here will be used to fix all the hazards with the BuggyFactorial example we examined in the previous part of this lesson. Once again, you can find this code in the EX2 project in the FP folder in my modern Java GitHub repository. The factorial method in the parallel stream factorial class functionally and correctly computes the nth factorial via a Java parallel stream. The first step in the factorial method implementation generates a stream of longs from 1 to n using the long stream range closed factor method. In this case, we choose a value of n to be 8 so we can visualize how the program behaves on the slide. We next call the parallel operation, which converts the sequential stream into a parallel stream. This has the effect of splitting the stream of longs into atomic-sized chunks. Basically, we'd end up with the original range of longs from 1 to 8, first being split up into 2 chunks from 1 to 4 and 5 to 8, then into chunks from 1 to 2, 3 to 4, 5 to 6, 7 to 8, and so on, until the chunks become atomic-sized and can't be split any further. The parallel operation also arranges to run these chunks using the common fork join pool, which has a pool of threads which are mapped to the underlying processor cores. So all the computations we see here will in fact run in parallel. The next step is to call the map to obj intermediate operation to convert the long primitive values into big integers, which of course are arbitrary precision integer values. The next phase of the parallel stream applies the reduced terminal operation. This terminal operation works in several steps. First, we use the big integer multiply method to pairwise compute new immutable big integer objects. For example, you can see here on the slide that the values 1 and 2 will be multiplied together to create 2. The values 3 and 4 will be multiplied together to create 12. The values 5 and 6 will be multiplied together to create 30. And the values 7 and 8 will be multiplied together to create 56. Each of those multiplications occurs sequentially, but they all run in parallel. So we end up with a set of computations that are taking place, creating those new values. The next phase in the reduction process is to merge two immutable objects together to create a new one. This takes place as the different threads finish working themselves sequentially and then have to reduce the results to provide combined values. So for example, you can see here that the results from multiplying 1 by 2 and 3 by 4 are then reduced to create a value 24. Likewise, we also see a reduction that takes the value 30 and 56 and reduces that by multiplying those values together to create 1680. And then finally, 24 and 1680 are reduced by being multiplied together to create the final value, 40,320. In this case, we're using immutable objects to create new immutable objects. It's very, very important that immutable objects be produced and used in this process in order to avoid chaos and insanity. And you can read more about the types of problems that occur by taking a look at the link at the bottom of the slide. So that's the end of our overview of the immutable object portion of key functional programming concepts and features found in modern Java.